All right, so we have developed an eye for detecting when an equation is explicitly stated, if it's in the form y equals something, where that something does not involve y. Here's an example of an explicit equation, y equals something. That something does not involve y. We also have a notion of implicit equation, that's all other equations, and these are not of the form y equals. Clearly this is not of the form y equals, well, this is an implicit expression. Now, we know how to take the derivative of an expression that is explicit. You've got the sum and difference rule, the constant multiple rule, the product rule, the quotient rule, the chain rule. You've got a bunch of tools for taking the derivative of functions explicitly. And you know actually if you took the derivative of this guy, it would just be minus sine x plus 10x. That's not too hard, frankly, at this stage of the game. But what I want to do is approach this derivative that we know the derivative of in maybe a different way. And a way that at first is going to be like, man, why would you go through those extra steps? Because we can cut to the chase with this, and we know that the derivative, hell, let me just write it out here. You know that the derivative is going to be minus sine x plus 10x. You know that. And you can get there in one step. But the different method that I'm going to use here is something that is actually going to allow us to take the derivative of functions that are stated implicitly. Because, I mean, how are you going to go about taking the derivative of this thing? How are you going to deal with that y squared? It's not exactly clear. So let's deal with this derivative, and let me do it again in a kind of a strange way. So here's what I'm going to do. Every time I take a derivative of something involving y, I'm going to tack on a dy to that expression. And every time I take the derivative of something involving x, I'm going to tack on a dx. So here's the way that I'm going to sort of strangely go about taking this derivative. And I'm going to go term by term. It's a weird thing at first whenever you think about it, but I'm going to, well, you'll see as we go through it, it's actually going to yield the same result. So I'm going to go term by term by term by term. If I take the derivative of y, I'm going to tack on a dy. If I take the derivative of x, I'm going to tack on a dx. So first term, y, take its derivative. The derivative of y is 1, right? Because just like if this was an x, the derivative of x is 1. You know anything of degree 1, you just drop off the variable and pull off its leading coefficient. So the derivative here is 1, but since I have taken a derivative of a y term, I'm going to tack on a dy. What about on the other side? Take the derivative of cosine x. The derivative of cosine x is negative sine x. But since I've taken a derivative with respect to x, I'm going to tack on a dx. Next, take the derivative of 5x squared, that's 10x. But since I've taken the derivative of something involving x, I'm going to tack on a dx. Take the derivative of 18, that's 0. Well, that doesn't involve an x or a y, so let's just call that 0. And in fact, hell, when you add 0 to something, you know that that has ultimately no effect. So the 18 just drops off. And now what are we looking for? We're looking for dy over dx. And how can we get this? Well, note, on the right-hand side, both terms involve a dx. So we could rewrite this by factoring out as negative sine x plus 10x times dx. And on the right-hand side, we've got a 1 times dy. Well, that's just dy, because anything times 1 is itself. But then you look here, and what are we looking for? We're looking for dy over dx. So what are we going to need to do to make that happen? Well, we're going to have to divide both sides by dx. But when you divide this side by dx, the dx's cancel. And then when you correspondingly divide the other side by dx so that you don't disrupt the equality of your statement, well, what do you get? You get dy over dx equals minus sine x plus 10x. Which is precisely what the derivative is. And again, you look at that and you say, man, that took a lot more work to go through those steps. But here's the thing. We can employ this tactic and apply, really, this tactic to a situation with an implicit equation. and take a derivative just as well. You can see in the explicit case you get the result that you expected with more work, but in the implicit case, now you have something that's doable. So, how are we going to go about taking this derivative? We're going to employ the tactic that we had over here, which is anytime you take the derivative of a y term, you tack on a dy. Anytime you take the derivative of an x term, you tack on a dx. So, go term by term through this guy. Take the derivative of the x squared. That's going to become 2x, but since you took a derivative with respect to x, tack on a dx. Plus, now we've got a y squared. You know what the derivative of 2y is, or excuse me, what the derivative of y squared is. The derivative of y squared is 2y, but since we took a derivative with respect to y, we're going to tack on a dy. Take the derivative of 1, that is 0. And now, you look at this expression, and unlike the previous expression, where we had all the dy's on one side and all the dx's on the other, and it was sort of easier to see how we could get dy over dx, in this expression, we've got dx's and dy's on the same side. So you sort of ask, how are we going to get this dy over dx? Well, after we take the derivative, the next thing we're going to do is we're going to put all the dx terms on one side and put all the dy terms on the other. And if we do this, I claim this is going to put us in a position where we can take the dy over dx more easily. So let's put all the dx terms on one side, all the dy terms on the other. So let's go 2x times dx. We'll keep that on the side that it's on. Let's move the dy term to the other side. And to do that, what would we need to do? We just need to subtract 2y dy from both sides, y from both sides, because you're going to have to do the same thing to both sides in order to keep the equality preserved, and in order to get rid of the 2y dy, we'll just subtract 2y dy from both sides. And now we get here. But here's the thing to think about. Since all the dx terms are on one side and all the dy terms are on the other, you can factor out a dx from all the terms on the one side. Well, in fact, in this probably only have one term, but so be it. You can factor out the dx, and over here, since all the dy terms are on one side, you can factor out the dy. And now, in order to get dy over dx, you want your dy to be by itself. You want your dx to be in the denominator. So first, let's get dy by itself. We could divide away by everything that dy is multiplied by. So next, divide away by everything multiplied by dy. And then that would be what? Dividing by 2y over here and doing the same thing on the other side, because you need to do the same thing to both sides in order to preserve the equality. But we're going to divide by 2y so that those 2y's cancel. That's going to give us dy equals 2x over minus 2y dx, because the dx had been previously tacked on, right? And now you say, okay, but we need to get dy over dx, so what do we need to do? Well, we've got the dy by itself. Now we need to get the dx in the denominator, so what we'll do now is divide both sides by dx. And if you divide by both sides by dx, you'll get 2x over minus 2y equals dy over dx. When you divide the left side by dx, the dx drops off. When you divide the right side by dx, you get the dy over dx you were after. I suppose we could simplify this very nicely because there's a factor of 2 in numerator and denominator. So to be very specific, negative x over y is dy over dx. But here's the long story short. The long story short is this expression was not explicit, yet we were able to compute its derivative. How? Every time you take a derivative of y, you tack on a dy. Every time you take a derivative of x, you tack on a dx. Then, through ordering and organizing, we can get the dy's on one side, we can get the dx's on the other, and then we can divide whatever's multiplied by dy to get dy by itself. Then we can divide the dx to get it in the denominator, and we'll have an expression for the derivative, which is something. That's in some sense a victory, because this was an implicit function, and now we have its derivative. And heck, I'm going to go through a couple more examples so that we see familiarity with this, and then we'll be off and running.